So in this one, they want you to identify two types of chemical bonding in the source of dietary potassium. So this is the source that we are looking at. So we can first, there are only three types of chemical bonding. There is covalent, ionic, and metallic. And so let's first eliminate what we know cannot exist. Well, metallic is between two metals, and K is a metal, but PO4 is not a metal. So therefore, metallic cannot be the answer. So the only two possible answers left is ionic and covalent. So in this one, they want you to identify the noble gas whose atom has the same electron configuration as a potassium ion. Okay, so we're going to go to the periodic table, and we're going to find potassium. And so potassium is right here. This is potassium right here. This is potassium. Now, potassium is a metal, and a metal is going to lose its electron. So when it loses electron, it's going to lose one electron. The question here is, when it loses electron, which noble gas is going to look like? So when it loses one electron, it now only have the same number of electrons as argon. Okay? And so it cannot look like a krypton. It must look like an argon. Another way to look at this is, what is the closest noble gas to that element? So in this case, krypton, the closest element, the closest noble gas is argon, and it takes way more traveling to get to krypton than it does to get to argon. Only take one versus a whole bunch of things. So that answer here will be argon. So in this one, they want you to compare the radius of a potassium ion to the radius of a potassium atom. So we already know that in a potassium ion, we lost an electron. And when you lose an electron, you become smaller. So therefore, the radius of a potassium ion is smaller than the radius of a potassium atom. Okay, so in this problem, they want to determine, they want you to show a numerical setup for calculating the percent error for the mass of potassium in this serving. So percent error is on table T, and this is right here is the percent error. And we know that we need to know what the measure value is over the accepted value. Okay, so the measure value is the amount that is right here, 172 milligrams. And the accepted value is 170, okay? So to do this problem, all we have to do is to write it out. Is we're going to say percent error is equal to 172 minus 170 over 170 times the whole thing by 100. And that is all we have to do, because all they want is a numerical setup. They don't want anything more than that. So this problem wants you to write empirical formula for glucose. Well, we know glucose is this one right here. This is glucose. And so empirical formula, remember there's three types of formula: empirical, molecular, and structural. This is a definition question, because if you don't know the definition of empirical formula, you can't do this. Empirical formula is the simplest formula. That means we reduce it down. So let's see if it's any less already. I'm sorry. This is the glucose right here. So glucose itself is C6H12O6. So can we reduce the factor here? And we can see that the factor can be reduced by 6. So if we reduce it by 6, we have C1, H2, and O1. And we don't need this one, so therefore we can write CH2O. And that right here is your empirical formula. In this question, it wants you to state evidence that indicate photosynthesis is endothermic. This again is a definition question. Endothermic means that you are absorbing energy. We see that photosynthesis is an endothermic reaction because light energy is on the reactant side, so it's absorbing energy. So your answer would be that photosynthesis is an endothermic reaction because light energy is absorbed. This question wants you to explain why the electron configuration of 2711 represents a sodium atom in an excited state. If we look at the periodic table, we can see that sodium has a electron configuration of 2-8-1. Okay, so therefore we can see therefore that this electron configuration that is provided right here for a sodium cannot be the ground state of sodium. So therefore what you're going to say then is that the configuration that is stated here, 2711, represent a higher energy state than sodium ground state. You have to show that this is a higher energy state than this one right here is a higher energy state than the ground state is. Okay, so again, you're gonna have to say the configuration represent a higher energy state than sodium ground state. Or you can say that one of the electrons in the second shell has jumped to the fourth shell, or jumped to a higher energy shell. So they want you to explain here in terms of electrons how strontium salt emit color lights. And so you have to remember that light is only emitted when an electron moves from a high energy state down to a lower energy state. Okay, so therefore you're going to say that strontium electrons from a high energy state move to a lower energy state will emit specific color. I'm sorry, specific amount of energy in form of light. So in this one, they want you to talk about how the bright line spectrum viewed through a spectroscope can be used to identify the metal ion in the salt using a flame test. So what you want to talk about here is the bright line spectrum and the uniqueness of the metal wavelength. So you're going to say then is that the spectral lines are compared to the known bright line spectra. Or you're going to find the elements that emit light with the same wavelength. Okay, so what we're going to say is we're going to find the element that emit light with the same wavelength observed. Okay, so we want to show a numerical setup for calculating the grand formula mass for reactant 1, and this is reactant 1. So with reactant 1, we have 2 carbons. Okay, so we're going to take 2, and we know that that is, that carbon equal to 2. Hydrogen is equal to 2, 4, 5, 6. And oxygen is equal to 1. And we know that this is 12, 1, and 16. We're going to add that up. That's 24, 6, 16, and we need to add them up here. So that will thereby give us 3046. Okay, but you didn't have to show that. All you had to do was show this setup right here. You don't actually have to solve for it. So in this question, they want you to say, in terms of molecular polarity, why reactant 2 is soluble in water. I don't care what reactant they're talking about. All you need to know is that water is polar. And if a solute dissolve in water, then that solute must also have the same molecular polarity. So your answer is pretty generic. You just have to say that both water and reactant 2, which in this case is methanoic acid, has the same polarity. Okay, that's all you have to do. That's all you have to say. You say both the reactant 2 and water has the same polarity, molecular polarity. So in this one, they want you to state the class of organic compound to which product 1 belongs. So we're looking at product 1, okay? And so we're going to go to table R that's going to give us the various different class. And if we take a closer look at this, we see that this particular group and this particular group is joined by this thing right here. Oh, so therefore it really is an ROR situation. So therefore, let's go see if we can find it. And lo and behold, there it is. This is ether, where we have O in the middle and 2 different carbon group on the side. So that is a ether.